Hello friends, today we will discuss our new topic, that is basics of IR spectroscopy. I am Dr. P.R. Mahalle, Assistant Professor and Head, Department of Chemistry from Led Bhaskara Singh Arts, Professor Narendra Gonde Science and Achalata Gonde Commerce College, Sakarkheda, District Bhana. So we will start our topic, introduction. Now, infrared spectroscopy involves the interaction of infrared radiation with matter. It covers a range of techniques mostly based on the absorption spectroscopy, as with all the spectroscopic techniques, and it can be used to identify and study chemical substances. The samples may be solid, liquid, or gas. Now we will see the principle of IR spectroscopy. The IR spectroscopy theory utilizes the concept that the molecules tend to absorb the specific frequencies of light that are the characteristics of the corresponding structure of the molecules. The energies are reliant on the shape of the molecular surfaces, the associated vibronic coupling, and the mass of the corresponding to the atoms. The study of the IR spectroscopy involves absorption of IR radiations, which cause excitation of the molecules from lower vibrational level to the higher vibrational level. But as the vibrational levels are associated with the number of closely spaced rotational levels, the IR spectra is considered as rotational vibrational spectra. Now, the necessary condition for the molecule to absorb in the IR region, that is infrared region, is to change the dipole moment. Thus, the vibrational transitions which lead to change in the dipole moment of the molecule are called as IR active transitions, otherwise they are said to be IR inactive transitions. For example, hydrogen molecule, nitrogen and chlorine, that is H2N2 and Cl2, does not result in the change in the dipole moment and are not absorbed in the IR region, and hence these molecules are said to be IR inactive. While in carbon monoxide or ammonia, there is a change in the dipole moment which causes the absorption of the molecule in the infrared region, and hence these molecules are said to be IR. Now we will see the types of the vibrational modes. The fundamental modes of vibrations. There are two types of fundamental modes of vibrations: stretching vibrations and bending vibrations. We will see the stretching vibrations. These are of two types. One, the symmetric stretching, and another one, the asymmetric stretching. For bending vibrations, these are of four types. First, the scissoring, next rocking, wagging, and twisting. Now we'll discuss one by one. First, the stretching vibrations. The change in the internuclear distance between the two atoms without the changing bond axis is called a stretching vibration. As we know that these are of two types. First, the symmetric stretching. In this type, the movement of atom is in the same direction with respect to a particular reference atom. And the asymmetric stretching means the movement of the atom is towards the center while that of atom is opposite to the center with respect to the particular reference atom. We can see the stretching vibrations in the adjacent diagram. How the stretching vibrations work. These are two types: symmetric stretching and asymmetric stretching. Now we will see the bending vibrations. Bending vibrations include the change in the angle between the two covalent bonds, due to which the change in the position of the atom with respect to the original bond axis. This is called as bending vibrations. These are of four types. Number 1, scissoring. In this type, the two atoms approach each other with respect to the central atom. Next, rocking. In this type, the movement of the atom takes place in the same direction with respect to the central atom. Third, wagging. In this type, the movement of the atom takes place in up and down manner with respect to the central atom. And twisting. The type includes one of the atom moves up the plane while other moves down the plane with respect to a central atom. These bending vibrations can be shown as follows. The bending vibrations are of four types: scissoring, rocking, wagging, and twisting, out of which the rocking and scissoring are in plane bending vibrations, while the wagging and twisting are out of plane bending vibrations. Now we will move towards the fundamental modes of vibrations. Now what are these? The stretching and bending vibrations are the fundamental modes of vibrations. The vibrational frequency of the bond increases with the bond strength. The molecule which contains n number of atoms will have 3n degrees of freedom. The total number of degrees of freedom is the sum of translational, rotational, and vibrational degrees of freedom. That is, total degrees of freedom is equal to translational degrees plus rotational degrees plus vibrational degrees. So how do we get the vibrational degrees of freedom? It is the sum of translational and rotational degrees deducted from the total degrees of freedom. For linear molecules, there are only 2 degrees of rotations, and thus for linear molecule containing n atoms, the total degrees of freedom is equal to 3n. The translation degrees becomes 3 and rotational degrees of freedom becomes 2, and therefore for linear molecules the vibrational degrees of freedom is equal to 3n minus 5. For non-linear molecules there are 3 degrees of rotation. Thus for non-linear molecule the total number of degrees of freedom is equal to 3, translational degrees of freedom is equal to 3, and the rotational degrees of freedom is equal to 3. So for non-linear molecules the vibrational degrees of freedom will become 3n minus 6. So the fundamentals of modes of vibrations of different molecules by using these two formulas can be calculated. Some of the examples are being quoted here in the table. For example, the molecules nitrogen oxide, carbon dioxide, water, ammonia, methane, and benzene. As per the calculations, the nitrogen oxide NO and CO2 carbon dioxide are the linear molecules. The fundamental modes of vibration for these two atoms respectively are found as calculated as 1 and 4. Water molecule, ammonia, methane, and benzene molecule are non-linear in nature, and therefore the applicable formula for these four molecules is 3n minus 6, and the fundamental modes of vibration for these four molecules is 3, 6, 9, and 30 respectively. So next, regions of IR spectra. These are the regions of the IR spectra which can be seen in these two types of tables. The regions of IR spectra is divided into three parts: near IR, mid IR, and far IR. We can see the wave number, frequency, and energy for the IR spectral regions. The wavelength for near IR region is about 0.78 to 2.5. For middle IR region it is about 2.5 to 50, and for far IR region it is about 50 to 1000. Okay, now we will move towards the higher absorption of common functional groups. There are different functional groups like alkanes, alcohols, alkynes, some nitriles. There are some aromatic compounds also, amines, and some carbonyl compounds which includes aldehydes, ketone, ester and acid. In the table we can see the absorption frequencies of these functional groups, and from this we can easily guess the absorption location in centimeter inverse, that is wave number. We can easily guess the particular absorption of that particular functional group. We can see here the general IR spectrum by which we can observe the different types of absorptions on the scale, and an example of IR spectrum of ethanol can be given for your illustration. The infrared spectrum of ethanol shows the absorption peaks of hydroxyl group, that is OH, in between 3000 to 4000 centimeter inverse, and the regions of alkyl groups in the regions for near about 1000 centimeter inverse. So friends, this is the basics of IR spectroscopy. Hope you will understand this basic, and I wish you best luck for this your further studies. Thank you.